material and form. And so 100 years ago, when guys like Maillard or Pierluigi Neri started to work and did their work, and later on Heinz Isler and Candela, the shell structures, engineers and architects. So for them, it was normal that they not just did the form finding and the calculations. No, they also did the processes. So many of them built also by themselves and had their own construction companies. To understand where we are today, what is the different thinking between architecture and structural design, I have a small sketch. So engineers are not trained to draw on a white paper. This is what you get trained as architects. So the first line, this is the conceptual line, this is the architecture line. The second line, this is the line of the engineers. So when there is drawn one line, the engineer can add the second line. And with the second line, you have to know all about what kind of material, what kind of structural system you will choose, what kind of material dimension you have. So if you throw a second line in a competition with an architect, you have to be sure that it works. And for a simple house, of course, it's something like I always saying, you don't need to calculate. It's about dimension, it's about proportion. So dimension about proportion, which you can do by really sketching intuitively the second line. But if you have more complex structures, just let's say a wider, large roof in a hall, so there are many options for the second line. So either you could make a rigid frame structure, or you could bring a joint in the middle, or you could just formulate this on one side, the rigid corner, on the other side, you have a slender column. And it could be in steel, it could be in wood, or you could do also a truss structure on rigid columns, or you could make a complete frame as a truss structure, like here in the famous Sainsbury Center by Norman Foster, one of his really early works in the 1970s. So this is, you have to have as an engineer, as a structural designer, you have to know all the potpourri you have in your mind when you do competitions with the architects. I show you now a few of my first projects, end of the 1990s and 2002. So when I stepped in the engineering company, Bollinger & Kromann, located in Frankfurt and also in more than 10 cities in Europe, but so outside of Germany, I was a young engineer after my PhD, and I was educated as a normal engineer, so know how the second line is done with normal structures and with normal material. And this was the time when the Franco Gehry finished his Guggenheim Museum in Bilbao. And this is, for me, it marks for me the beginning of digital fabrication in architecture. So I had the chance just in 4 years to work on 6 projects in Bollinger & Kromann, and they were all named in the so-called freeform architecture period. So also Zaha Hadid and Cracklin and all these guys came up in that time. And I like to show you now a few examples what it meant as a structural engineer to work on those complex geometries and forms. So this were the conceptual lines of Franco Gehry for his projects. I show you this now, this Mart A building here, which was finished in 2003 in Germany. So can you imagine to do the second line here as an engineer? I could not in that time. So I had no idea what this would be and how it should work. But the good thing was that Franco Gehry also, he did his whole design in large physical models. And before we had the digital tools, he was not able to realize this ideas. He was already around 60 when he worked on the Guggenheim Museum, because the digital tools were not existing before. But with the new digital tools, he had the chance to digitize the physical models. So today we have all these digital scanners which are able to scan everything in a high precision. But in that time, 25 years ago, there were a kind of a dot scanner. So manually, the people had to touch the surface of the model, and you got one digital point. And you can imagine it was on the precision on the people, if you have complex corner, how many points they did. And the digital models, they were totally, how do you say, fragile. So there was a lot of processing afterwards to make the surface smoothen and make this as discrete models. And Geary worked in this way. He designed the outer layer, the outer design of the architecture, as well as the inner of the space. But these were totally different designs. And with using CATIA from the aircraft industry, it was possible to bring those scans into 3D construction software. And this was also the start then to prepare steel structures underneath, which could support then the whole facade elements. And as an engineer, you see the blue line is drawing by myself. So you got from the architect the outer skin, you got the inner skin, and you had to find your structure. So there was no idea about structural optimization or structural efficiency. It was just about geometry. So what kind of structures fits in, and then of course you had to calculate. But you see, most of the work here on the right side was about researching on the geometry and also thinking, okay, you wanted to avoid double curved geometries, because how you manufacture double curved geometries in steel or in concrete and other materials. So this was a very, very complex work in that time. This was the starting point also for me to step into digital manufacturing and digital fabrication. So from that time on, I was fascinated as an engineer to work with those techniques. The second project I did with Bernhard Franken, here was different. Bernhard Franken is in my age. And this was for the BMW Motor Show 1999 in Frankfurt. It's the so-called bubble, water drop. All of these projects are good published. If you want to, you can research. You can go to ResearchGate also on my profile. There are a lot of them. And those pavilion, imagine this was in 1999 to express or to show driving with H2. So it was also 30 years ago, people were much more forward, also thinking in what is possible in car industry. And so Bernhard Franken, he used Maya to find this form, two water drops coming together, and by the forces of adhesion, and they wanted to go to one drop, but he stopped then the form finding, and this was the final model and the CNC milled wooden model. So for the engineers was nothing to do. So exactly this shape should be realized. So of course we did calculate and how you build a water drop. So in that time, our job was totally new, to find a manufacturing procedure or a manufacturing process to realize those forms. So the structural calculation, I would not say easy, but this was our normal job to do. And here you had the red area, the main stresses. Okay, this defined the thickness. And we used then acrylic glass panels, 1.50 meter by 3 meter. No, 125 by 2.50 meters. And so here you see with CATIA, the surface paneling. So we had over 300 elements, all different in geometry. And then we developed a manufacturing strategy using foam, PU foam, which was CNC milled with a five-axis milling machine. And we tried to bring on one element 4 or 5 different sheets with a similar curvature, so to minimize the waste for this manufacturing. The panels were heated up in an oven by 160 degrees and was around 150, 180 kilograms, the panels. And then they were laid down on the PU foam and then brought back again to the CNC mill to cut out the exact precise piece. And originally we were planning to glue the pieces together. You see the wooden scaffolding. This was just for the supporting structure. And then we want to glue, but you see here the open spaces, so 3-4 centimeters. So here we learned that the machine is really precise working, and if you do not precise work in the other process steps, then you get a problem. And so we had really a big problem here, and then we decided, okay, the wooden structure just for supporting, we use this now for the primary structure. And then from one day to the other, we started to water cut in aluminum the primary structure and just assembled the deformed acrylic panels on top. And this was also very, very nice. So without having this primary structure, this pavilion maybe would have been a really ingenious piece. But with the primary structure of aluminum, it gets much more an architectural piece. So the space inside was unbelievably nice. And this was also the precondition. With this knowledge, we could do then the next project, the Kunsthaus in Graz by Peter Cook and Colin Fournier. Those architects were from the 1960s, Archicram. So they had ideas about the first trip to the lunar, and how spaceships landed there. And this was now 40 years later, they were able to realize by the digital tools their ideas of a spaceship landing in the middle of Graz. And here you see, this was again a different procedure how to get to the digital model. So they molded this model out of acrylic glass as a small model, and we decided not to dot scan because it was not too precise enough. So we started with Rhino as the engineer to build up a new digital model. And also we immediately decided to separate primary structure and the acrylic sheets. But in difference to the motor show pavilion, this is really a museum. So you need much more layer and it should stay for decades, whereas the pavilion was just for 2 weeks. So we had to do a lot of other works. You see here technical installations, because in this historic part of Graz, acrylic is a burning material, so we need to sprinkler underneath. And you could imagine how complex this was to manufacture under the acrylic panels. And already in that time, around 2000, we started. Today, it's normal to have BIM and to do collision control, but here we did it in Rhino. You know, we took in all the different layers from the different partners, acrylic, pipes, insulation material, to see that there is no, and to control and to guide that there are no collisions. Here you see how complex. Yeah, and then in 2002, I got my first professorship in Kaiserslautern, and I decided with 2 partners to find my own office for structural design, because I was convinced this will continue in that way, so that now we, in the next years and decades, just build those kinds of architectures. But yeah, I had to see after years that this was all much too expensive, and so clients stepped back to build normal stuff, and also we had to build normal stuff, but with really good architects. We did a lot of interesting, nice buildings. And this were, I'm always saying, this were the buildings we needed for earning the money. And we were awarded, like Philip said in the introduction. But those smaller, more engineering pieces, these were the ones where you bring in more passion, of course, because this is, here you see the structure, and especially roof structures in wood, in glass, suspended, folded. So here is the whole materiality and processing integrated. I like to show you two project more in details. This is the observation tower we did in Austria, in close to Graz in 2008 to 10. So this was with a landscape architect, Klaus Löhnhardt. And so, like I said, the white paper, the conceptual line is the architectural line. Of course, today you rarely use a paper. So the first concept was to have this like in DNA, people go up, cross, and go down in a really curved line. You see there's just one line, is more a sketch than a structure. And then the architect wanted to have these bended tubes. But I showed him, look, we did already also for BMW 8 years ago for the pavilion in Geneva, double curve profiles. You know how you double curve thick profiles of 30 millimeters in diameter? No, I don't know. So I said, listen, we also built a model and a Rhino model. You cannot, there are really rare bending machines, maybe in the ship industry, but not in the construction industry to double bend or to double bend profiles. And so we used, together with the company, we developed a principle so that we just we selected we cutted the whole double curved geometry into one-dimensional band sections, and then we produced these one-dimensional pieces, and then in a own constructed three-dimensional space we were able, by turning the profile, by defining the angle of how you have to turn it, we got the second curvature. And this was then the secret that we could do this. And also you see here how's the joining principle, the joining principle between two profiles. So also here we developed details, but this for the Moore Tower would not be really cost effective. So we decided, let's do it in this way. We do a more polygonal structure, so that the redirection we do in the knots. So, and I believed that this would be easier, but at the end it was also not really easier, because every of the knots was different, and so really complex how they meet. So the architect wanted to have not that they come together in a complex surface. He took out the material here, and then we had to bring it on top the material inside. And so each of the knots was a kind of a puzzle of two-dimensional CNC cut plates, and had to be then assembled and brought together. But finally, it was is a really nice project. If you are there near Graz and want to see it, it's worth to go there. And also from that time on, and also earlier, I saw that the knots, so how the pieces are connected, these are always the geometric, most complicated parts. And so there you have to find a solution, how you connect pieces. And if you have this solution defined, then you can start to build up your structure. So here we did another small, really nice pavilion in wood. And also here, you know, each of the knots were different, and we did highly precise welded steel pieces, which we integrated then in the wood, like you see here. So the steel pieces, each one is different. They got all a number, and here we connected them with the wooden beams. Here we have special knots. You see they are much bigger because they have to carry the bending moment here around. Yeah. This is a project, one of my last project. I stepped out in 2019 because of our intense research. Also here this was an idea by me also as an engineer, you know, the architect's 100-meter long roof for a bus station, and they did regular columns, and I addressed the idea here. A column is not just a supporting element. The column could also be a spatial element. If we make the column bigger, if we give more space for the column, so then inside you have a space to integrate something or to bring light on the ground of this bus station. And also here the profiles are CNC cut, and then we used a membrane structure which we fixed on this ring, this oval ring, which is around here, and then we tensioned them along the columns and fixed them there. So here you see the membrane is fixed here on the continuous line, and here we integrated the line so that we stressed the membranes against these columns. Or here, each project is different, you know. So here we should do a connection bridge between two existing buildings. And so it was not 30 meters, was not possible to span over 30 meters and bring then the vertical loads here in this house and facade and on the other side. So they were not designed for this. So we decided to do the whole foundation in the middle between the four tracks of the street, and then cantilevering to both sides. So this is a cantilevering structure. The whole space is a profile, and people can go through it and have a really nice feeling about this. Here I got clear the first time. So when we tried to bring tube profiles 5, 6 together in one knot. So we glued 5, 6, 7 lines. We welded together. And so here I got the first time the idea, okay, if we continue welding, why not print the whole knot? So why we stop here and don't continue? So, and this is also a research project we do now in the last years. I will not present today, but in steel, we try to print the most complicated parts, the knots, and then we continue with normal standard steel profiles. So now in the third part, I show now our work on what we do in the Institute of Structural Design. I think also Norm presented some of the stuff already here in Shanghai at Dongxi last year. But like Philip said, so we are architect engineer, and we have, of course, also for the same piece, different perspectives. So I'm really happy to have the chance to, or had and have the chance to build up amazing research infrastructure since I moved from Kaiserslautern to Braunschweig in 2011. And being the spokesperson of this collaborative research center, Additive Manufacturing and Construction. By all the nice projects I did in my own practice, it was always project-based. So going from project to project, finding new solutions, new manufacturing procedures, and the next project to start again. So it's totally waste intense, it's consuming time, and it's really not economic. So you see that the normal construction is still manually on site, and we can do everything here, parametric design and building and information modeling, simulation, everything digitally. But here they need drawings. They need just PDFs on site. And this is what we have to change. So my passion is now really to go into new digital construction sites. And by going so, you have also to understand how construction industry is working. I'm not sure if there is a big difference to China. We have a discussion later you can mention. But let's say in our environment, so compare the construction industry compared to the car industry, for example. So car industry is a centralized production. So there is one location, BMW or Mercedes-Benz, or they have one of Volkswagen, small cities where all the pieces are brought and assembled, but also the design is done from the beginning, and you pick up finally your car here at the end. So they control the whole process, and they also create high productivity because of this control. And in this kind of end-to-end production is also not just possible. So it's clear that every new innovation is integrated. So it's really clear where you integrate Industry 2.0, 2.0, 3.0, 4.0. So when new things are coming up, they get integrated in this end-to-end production and get more efficiency, more productivity, earn more money by selling the cars. Construction, we are decentralized. So our factories are the construction sites. We have in Germany at the same time 200,000 construction sites at the same time. Most of the companies have 90% have less than 20 employees. And each project, there are coming so many different companies together, so there is no success for the whole object. Each company tries just to get their own success, but there is no increase in productivity. And we have fragmented processes between planning and manufacturing. So we first plan, then we try to find the companies and manufacture. And how you integrate innovation. So if you plan and you do something which is not state of the art, so the client asks, okay, what will this cost? And you say, I don't know. We have to find a company, like in this pavilions I showed before. So the client in that time said, okay, look, I will pay. But nowadays, nobody says, no, I don't want to know now what it costs. And if you do a planning and then standard planning, and then no construction company will come and say, listen, we can make a nice project. We can 3D print this structure. Why they should do, is risky. So it's really complicated to integrate innovation in the construction industry by the construction industry itself. And this you cannot change. So you have really to see how you bring in innovation here. And my opinion is clear. We need to move away from this just project-based perspective, and we have to get more in a process-based approach. So we need to repeat processes, but they have to be adaptive as a process, so that we have also customized or individual outcomes. So we need in construction a kind of automation, but not fully automation. So I always say we need digitalization in manufacturing, but still individualization in the outcome. And this is different to car industry, which is serial production. And additive manufacturing, we are considered, is one key technology for this approach, because additive manufacturing is a digital technology and you have a customized outcome. And everything is there. So we have, over the last decades, a lot of advanced materials developed: ultra-high performance concrete, fiber reinforcing concrete, textile concrete, different kind of wood wooden materials. And we have all the sophisticated computational tools. So the digital technology has to be able to connect all this research which was done the years and decades before. When I say we, then this is the TRR 277, additive manufacturing in construction. This is a DFG name because we are number 277 in the funding history. And this is running since first of 2020. And we do this together with TU Munich, TU Braunschweig, and TU Munich. So why additive manufacturing? Additive manufacturing, you see on the left side, the column is the most complicated or formwork intense part in construction. So a wall, a slab, you have or a beam. The column a column has 4 sides which you need for formwork, and here you see that when you do it, So when you print a column, you don't have a full profile. So here, the whole formwork is filled with concrete. If you print a column, you just print a ring. That means it's much more effective. So you have less material, is more effective, and you have the inner space to use this space, for example, for post-tensioning, which we did here with this column. And you're able by 3D printing also to try to find new designs. For example, if you have this part where the vertical goes to the horizontal. But what is additive manufacturing? And this is important for me to know. So additive manufacturing is not robotic assembling. So what Kola already 20 years ago did, they started to assemble these bricks by using a robot and to get these freeform structures. This is robotic assembling, but not additive manufacturing, because here already the material is in a preform. It's a brick, and a small brick, but the brick defines your procedure. In additive manufacturing, you bring the material into form during the process. So the material is plastic, and you form it by the application. And this is a difference. Why? Because you have just to control the robot, the geometry. Here, you have to control the robot with its geometry and the material with its hardening character during processing. And this is a different thing. Here you see you have two sides to control. Here you control the material. Here you control the robotic application. When we set up this collaborative research center, so we formed 3 areas. Area A, this is the basis, materials and processes. Here we choose different materials, I show in the next slide, and different additive manufacturing processes. So the material process interaction, this is the most important thing on the area A. To make the processes robust, you need computation modeling and process control. This is area B. So area B compares area A. But we want not just to develop new materials and new additive manufacturing processes. No, we want also to implement them into design and construction. So how they are interacting with the phase of design and the phase of construction as a digital technology is very important also. Here you see area A. So we have 5 different concrete technologies. Mineral composites means mineral-based as concrete and steel, both mineral-based. This is why mineral composite. We have also earthen material. We have fibers and filaments, and we have metals. And then we have different technologies, particle bed and deposition. Here you have particles where you build up a particle bed, and there where you either with a laser bring in heat, or here you bring in fluid water or cement lime, then you harden exactly just where you position the material. And then later on, you can excavate the material out of the form. And so here you are able to make much more geometric complex and with a higher higher precise pieces. Extrusion is the material is already mixed, and here we have the different technologies: the extrusion, then the spraying, and the injection, which I show later. This is the B area, and this is also very important. So digital, the digital connection between planning and additive manufacturing is not just a substitution, so that you now, the analog processes on site are substituted by digital processes. Now, if you have a fully digital environment, then you have the digital twin, and you are able to totally different communicate between design and construction. So you don't need to do first the whole design and then you give it to the construction site. You can already start with a design, give it to the construction site, and then when the construction site is manufacturing the pieces, there is sensor control all over, and you get the information back to the design. And if there are some failures, if there are some differences in the geometry, you can now also adapt the design model, not just the construction on site. And this is totally different than 20 years ago when we worked for Franco Gehry and Peter Cook and those guys. So what makes the TRR 277 really unique? So what is the unique thing here? And so of course, first is a highly interdisciplinary teamwork. So we have architects, engineers, robotics, informatics. So different disciplines, and they have to work together. And this makes it really unique. The second thing is that we have this outstanding research infrastructure at TU Braunschweig, but also at TU Munich. So here the DBFL I show later again, 14 meters in length, 7 meters in the width, and up to 3 meters in height. This is from the stone industry. So a CNC portal, which forms the basis. And here we integrated a second portal with a Stolpe robot. And the tricky thing is we have robot and CNC control in one environment. And this is not what you can buy on the market. Normally you have 20 robots or you have CNC, but not the combination. We have also mobile robots, which are now integrated in the setup. And here the particle bed printer for steel. And this is new since last year, or this is turned. We have the so-called digital construction site. I show also later a little bit on this. So outstanding research infrastructure, highly motivated and interdisciplinary team. And how they work together. They work together, and this is also something unique on really large collaborative demonstrators. So the experiments, the experimental part, the demonstrators, they are the core where all come together. The design is done, then the things are printed, then they are sensor control, the feedback is given back. So on each demonstrator, always more than 4, 5, 6 projects are involved. And here you see, for example, this is what the guys from TU Munich do. This is a facade element. Why is this now? A facade element, 1 meter, 25 by 3 meter. And so this is designed, each of the elements could be different. It's designed to the shading. So the whole geometry is related, the angles to the shading where they are located in the building. And then they are also porous inside so that the insulation material could bring in, but also installations and air could circulate within the element. Here you see this particle bed. So it's a huge bed. So this is 4 by 4 meter where this element is in. And no, it's not 4 by 4. It looks a little bit smaller, but I think in length is 4 meter, and in the other direction is 2 meter. And here we also integrated on the back an area where we could bring in concrete. So concrete and reinforcement, so that this element is really able also to carry loads and doesn't need another primary structure. With this technology, we also start now to do new building designs. So you see here that a brick could be totally different, defined for the future. So a brick could be much larger. A brick could have 3 meter to 2 meter, or 3 to 4 meter. And by using tri-joints, which is also part of our project, we also have something for design for deconstruction. So also we are able to deconstruct later on these pieces. And you see here on the left, on the right side, we also can integrate then hollow spaces for circulating air, so that there is no additional insulation is needed. So this is the old traditional hypocausten system, using air to circulate and to fulfill the heating performance. Also, bridges are possible. Here you see how the pieces are excavated, and they have also here this small part so that they could stick in together. And also this structure is post-tensioned. So we have spanned the cable here inside. We have hollow spaces so that the bridge is suspended. Now I go into detail into two technologies, which we focus on the ITE, and Philip already mentioned. So Norman and me, we lead the institutes, architect and engineer. And we have also then from both disciplines our staff. And it's interesting. So architects and engineers are different, but after a few years, they start really to understand each other also. So here you see our setups, which we mainly use. So the DBFL and digital construction side. And these are the technologies we have developed. So shotcrete 3D printing, large particle printing, injection 3D printing, hybrid WAM, robotic rammed earth, concrete sprayed earth, and wax formwork. And now also with you, Philip, we do now workshop on selective ramming. So this here is more in a ramming by a surface, by the whole thickness. And by using a smaller rammer, you are more able to do geometric complex pieces. So I focus on the shotcrete 3D printing, and this is a technology where high-tech material and high-tech process and high-tech form finding has to come together. So originally developed 100 years ago, we set up this as a robotic process. And you see here, it's like extrusion from the outer appearance, but inside is totally homogeneous because we print with pressure. We integrate air pressure here. We speed up the material and we get a mechanical bond between the layer underneath, and then this is why it's homogeneous inside. We have now since 3 years, an automatic mixing plant added to the DBFL, so we can control completely digitally the material flow and also the robot. So this is why I say material process interaction digitally controlled. Here you see the freedom we have with the shotcrete 3D printing. So we have a robot with 6 axes plus the portal with 3 axes, so 9 axes. So we are free in geometry, but we also have the laser tracker. You see here, if we have some failure, so then the laser recognized, and then automatically the laser, the speed of the robot gets adapted to the missing piece, and after 3 lines, it's filled again. So I said, yeah, we are free in space, and how to control the geometry, different options. There are also publications you see. I don't like to spend too much time here. Because we have to bring out the stuff. We could not do a house here inside in our lab. We have to bring out by our crane, and then we focus on pieces, one-to-one pieces. But the most difference to all the extrusion technologies is the reinforcement integration. So we are able to integrate the reinforcement in the shotcrete process, and we see this as an integral part of the digital fabrication. So they are interconnected, and either we first spray the concrete and then we just put on the layer, or I show later other technologies to integrate the reinforcement, or we start to first weave some fabric, some structure, where we spray on top a thin layer of concrete. This is more what Norman is doing, and I show later a few photos where he's also focusing on. As a structural engineer, not each of the pieces have to be topological optimized or have to form along the bending moment. No, you could also have a normally beam with a normal rectangular section, but the reinforcement integration could be really along the tensile forces. And this is what we do here. So we calculate where are the tensile forces, and then we print the concrete in that way that the concrete supports the reinforcement in its application. Here we used thin carbon fiber layers, which you see here from the outside also. Yeah, here you see what we often use is the second layer printing. So we can also bring reinforcement in front of a printed piece and then print a second layer, and we can smoothen the surface like you see on the right. And here in 4 hours, it's a double curved piece, fully reinforcement and with a smooth surface done. So you will never get this with any other technology. We have developed different technologies to integrate reinforcement. So the normal thing is maybe here on the right side that you lay it down on the layer and then you print again the next layer. But we also use robot technology so that we screw reinforcement inside, short rebars. And this is possible because the concrete is still in a green state. And there's a lot of research how long this window is open to screw. And then you could do vertical reinforcement, but not one reinforcement, not one rebar with a length of 3 meters. No, you have one rebar with a length of 3 meters with 10 pieces of 30 centimeters, or 40 centimeters. We have the overlapping. So this is how it works. And this is what we just erected a few weeks ago. So we also go now outside the lab, really slender, 10 centimeters, single curved wall for an animal shelter, which stays here and which we prefabbed. And here the reinforcement is also integrated. We have developed another technology. So not to just put the reinforcement before, first we mill or we scratch out such grooves so that we can integrate the reinforcement. We win 2 or 3 centimeters with the thickness, and we fix it here by a pneumatic shot, so that then the second layer print is done on top. And this could be also along the tensile lines. Yeah, and here the idea is for new forms, housing is one thing. We print now houses in Germany, so with round corners, but a house is a house, and many people have normal furniture, and then they want to have right-angle corners. But for coastal protection, for example, we work with my colleague, Niels Goseberg. You could already, the form finding could adapt part of the water energy. And this is something which is totally new for us also to step into this environment. Dirk Loke, I was in also part of this. We did a night publication on digital fabrication strategies beyond planar horizontal layers. So here, if you want to check this, we did a nice paper on what is possible with 3D printing in concrete, what kind of geometries, what kind of strategies you could choose. We go more and more also now in hybrid structures. So not just everything has to be printed, but we concrete, for example, thin slabs of 6 to 8 centimeters instead of 30 centimeters, and we print on top ribs. So this was the guys already 60, 70 years ago did, but they used formwork, and this is too expensive today. But with this technology, we can come back. Here you see a normal a slab, a single span. So we are able also to form the beam along the bending moment. So we vary the thickness. It's a curved profile, is not just the same thickness. And we integrate the reinforcement exactly where it's needed. And then you turn around 180 degrees, you see here, then you have a slab and a on top printed rib. We did also we do some life cycle assessment. So here you see that with this solution compared to a 60 centimeter slab for 6 meter span, we save close to 40% concrete, close to 40% CO2, and close to 50% steel masses. This printing with shotcreting is also possible for really filigrane structures. So because on this mechanical bond between the layers, if you just print 4 or 5 layers and bring reinforcement inside, you see we can do this nice grid shells or truss structures, spatial structures, to have totally new ideas for also for structural design with concrete. Or here, the next step that we really connect form finding with path planning and printing. So that means if we have a section and we arrange columns in that way, or we change the arrangement of the columns, or we change the form, so directly then we get the stress lines for the reinforcement, we get the path planning, and then we could already print these pieces. This is what Norman is more doing. So that the reinforcement is done first, and the concrete is applied on top. Let me check if I see it again. Yeah, here on the right side. And here you're able to do really thin shell structures of a few centimeters if you use carbon reinforcement, and really elegant, slender structures. I just took in here this image. Maybe you know this as Yokohama Port Terminal in Yokohama in Japan, from Foreign Office Architects. So this everything was done in steel, but imagine you could do this now in this kind of technology. This is also what Norman is more focused on injection 3D printing. So this is the most lightweight concrete printing technology we have developed. We have patented partly in Braunschweig. Of course, the reinforcement is a challenge here. So how we get it reinforced, because is really sensitive. It can crack, break, and this is why compression only is one solution to find designs where we have less or no tensile stresses. But we all know for asymmetry and for transportation, we need to find solutions. And here, Yinan is involved. Yinan Jiao, he is now in Hong Kong, and he did his PhD in Braunschweig and did amazing work on this. Yeah, some ideas how it could look like. So finally, let me go to the robotic rammed earth. Are we still in time?
Yes, go ahead.
Yeah, okay.
Good.
So we have this robotic rammed earth, and if you now work with earth, it's not ultra high performance concrete. So you have low tech material, but a high tech process. And the question is also on how you get high tech form finding. And here the most interesting thing is it's so minimum, the material, granular material and clay as binder. And this exists for thousands of years. So you have to understand really how it works. And the whole procedure is the traditional procedure each step has its meaning. And so in the end, to make the water humid, but not too humid because it has to dry. The water is just for processing. Afterwards, it should harden again, should go out. So you try to minimize the mixing, the addition of mixing water. Then the layer thickness, how you get the information that the compaction is done. And also the formwork. And when we checked years ago, 8 years ago, we started to 18 or earlier, 17, how traditional rammed earth constructs today's process are working. So you see on the right side, they have a climbing formwork. Why? Because after compaction, manual compaction, immediately you have a green state which allows you to immediately remove the formwork. And then the material can dry because it's on the air, the outer surface. We were clever for decades ago. We use now the concrete formwork. So the whole floor plan we erect with concrete formwork, and then inside we fill in the material and compact, but we don't remove. So this has two mistakes. One is totally cost intense to erect this whole concrete formwork. Second, by not removing, it cannot dry. So it's stupid what we did. So we said we have to come back to the original idea, and we try to bring together formwork which is just needed during compaction, and then we have this climbing, this movable formwork which is adapted at the robot. So we have, you see we have copied again the traditional climbing formwork now in an active formwork guided by the robot. And then we have developed further in the last years also so we go much lower. We go just 2 centimeters of layer height, and we don't get higher compressive strength, but we get a much lower scatter. So that means we can allow much more of this wall to carry loads. And so the control of the application of the material is also done digitally. Here's the small movies. The feeding is done manually, but the application is done in a controlled way. Very precisely. And here you see then the compaction. Here we used a plate. Now we go also with pneumatic stamper. So different technologies, both is possible. We also start now with spraying earth. This is one of our research projects within the TRR. And here the material is much more humid, so you get much more crack during drying, and we add fibers. So we have this fiber shop. So we cut the fibers directly during spraying. Here you see the endless fiber, which is cut here. And this has two positive effects. One is it hinders the shrinking. The second is the fibers have connected to the outer side, so the drying it increases the speed for drying. And also here, this is also done by Inan when he did, before he came to Braunschweig, his master thesis at Aalto University with Tony Kotnik and Pierre Fricker. So things are possible to do then with for high water to guide also here to reduce the energy, the speed of the water, and to prevent villages. So what's next? Next is to go on the construction side. And like I said at the beginning, so we have developed a new thing. So here, this is brand new, that extrusion, but we can also hang on the spray board here, and we have added a second facility so that we can also do cooperative processes here. And something which are working on is here to work with is on Norman's former idea, which he developed at ETH, mesh mold, so that the meshes are done with robotic manufacturing, and then we fill in and the concrete, we spray in the pieces robotically. We work also with mobile robots here. So one is printing, the other one here has a sensor to touch and to control the green hardening and so on. This is research. But what is for us really important, you saw that we will keep the construction sites. So we will never come to a centralized manufacturing. So our construction sites has to get more digitized, and we will also keep the people in the loop. So not 3 or 10 robots, people and machines have to collaborate. And this means people have to integrate in the digital environment. And this is possible by augmented reality, by sensors. So this we call construction industry 5.0. So we don't step into 3 and 4, we immediately go into 5. And by all these sensors, we are able to work with our partners to control then the procedures. And stuff like, for example, reinforcement integration, this is just to put down, this could be done by one person. Never you would program a robot to put a reinforcement piece on a concrete layer and then print again. So the path planning for the concrete is done digitally and by a robot, the printing, but the reinforcement integration could be done manually by digital control via augmented reality. And if we do in this way, then also we have the information later on for the period of use. So we have all the information, what is inside. And so the whole digital model is also for maintenance and later on. Yeah, thank you very much for your attention. Was a high-speed presentation, but exactly like we defined. And now I'm happy to share some questions.
Great. Thank you, Professor Kloft. I think it's a fantastic lecture. Introduce including your career as a structural engineer all the way to be the leading professor in University of Braunschweig. I think it's really a mind-blowing lecture for this kind of cross-discipline, interdiscipline research, which is always, I think, is a frontier. In Germany, actually focus a lot, not just on design itself, but also introduce material science and introduce robotic fabrication, all the way collaborating architecture design and structure engineer design in the same platform, actually, which is supported by DFG Alert and also collaborated by different background, including practitioner from industry all the way to the university. I think it's very German, very German, very German style, because it's really difficult for the other universities or countries to follow. But I really appreciate because we can see a lot of a very experimental test in the discipline which is happening. And you mentioned the AMC, that's the special platform you established over the years. And I think the question will be a lot because you're doing so many things over the years that is very experimental. I want to ask you, because as a structural engineer, I find it's quite a big difference between Chinese structural engineer and German structural engineer. Here, we have a very big structural engineering school, and their focus is more on the not the graphic static, but it's a dynamic graphics to the SESMIS simulation, and also focus a lot on the nodes and the details to design for the high building and also the complicated structure system. But in our architecture school, we're a little bit similar to yours. What they're doing, actually, we focus more on the systematic and the material process of the design. So I want to ask you this kind of tool style from structure engineer perspective or from the structure design perspective. So how you consider this kind of research, which can connecting directly to the practice market, including the last time I met Manfred in Frankfurt, Frankfurt, and in his office, actually a lot of super big,
Manfred Krohmann, yeah?
Yes, Manfred Krohmann.
Yeah. This is I was Bodding and Krohmann, yeah. This office, yeah.
He's a great guy, and he picked me up last time from the airport.
Oh, really? We are friends, yeah.
Yeah, all the way visit his office. I think spend like half a day to visit his office. Fantastic office there. I think they are very practice driven, from his office. But still, you should facing a lot of problems. And 2 weeks ago, I talked to Guy. I think he is also doing some very similar things like what you are doing. It's very architectures engineering. I think it's not a very structural engineering. So I want to ask the situation in Germany or Europe, how you address such kind of very architecture thinking into the structure design process, is how you build this kind of conceptual design that is structure and performance conceptual design in the whole process, and how you will consider which part is important to design very engineering from the seismic simulation or this kind of detailed design, or the whole system from aesthetics perspective and the process perspective is more meaningful. So that is my first question. Would like to ask you, how would you like to address your research in the whole both academia and industry collaborative?
Yeah. No, thank you very much. This is really being here again, and it's a great chance to present here. And it's very German, yeah. On the other side, I really have to say, I think the collaboration is really has a really big potential because our problem is the transfer. You know, we are really good in fundamental research, and but transferring this into practice is really a big problem. And so we have the same engineering environment. And the good thing in Braunschweig is we are one faculty. So architects and engineers are in one faculty. And I was also years ago dean. So we are sitting together much more than maybe other architecture and engineering faculties. They are more separate. So we have to work together. And but at the end, all the engineering faculties, they are more structured regard to the materials. So we have concrete institutes, we have steel institutes, we have institutes for wood, and then we have institutes for sophisticated static tools, you know. But none in a building all comes together. So, but this is why students, they get really focused. Either they could do concrete, or they could do steel, or they could do wood. But what we need here in offices like Bodding and Krohmann, and also how I got educated, when we speak with architects, we have to know all about the materials and the systems, but not in the deepest detail, you know. Finally, and this we got lost this intuition, you know. The structural behavior is not different than thousands of years ago. So that didn't change. The physics don't change, but the tools change, you know. And by doing a single beam calculated by a computer today, you get 10 pages. When I was educated, you wrote it on half a page, you know. But by having experience, I don't need to calculate. I know how thick a beam will be or a slab, you know. And this is what the students get not trained today. And this is the major problem. And then our colleagues go more and more details, so more sophisticated tools. But in each building is a new project. there is no money, no budget for using these tools. So this you can do in a centralized production. So when you do serious, you have a product, then you take out every gram of material and you try to optimize here and there, but not for a house. Come on. Yeah. Maybe in bridges is different. Really large scale structures, high rises is also a little different. But this is the main problem. But I see now by starting with this really interdisciplinary work and this experimental work. So this is also, I didn't present something which I would say is a unique procedure. So normally you start to do deeply fundamental research, and finally you do a demonstrator. It's a little bit same like in architectural design. So you do a lot of digital, I don't know, parametric design here and there, and finally you do a final nice model. But you should do the model much earlier, because then you see the spatial qualities, then you see, and this is exactly, so we at the beginning we start in a 1-to-1 with a proof of concept. So we have an idea, we say, okay, this robotic round earth, it could work. And so we start to do a wall. And so everyone is fascinated, wow, it works, And then we start to go deeper and deeper, understanding how to control. Not first we have everything research and then we do a final demonstrator, a wall. No, this is it's a kind of a loop,
Great. I think it's kind of demonstrators we name like mockup, and also
Mock-up. Yeah.
yeah, the pavilion culture is super important. I think we're also learning a lot
Yeah.
from German universities as well as like AA in London. They are doing a lot of this kind of mock-up pavilion. I think the pavilion will be some like demonstrator, as you mentioned, to prove a lot of like evidence-based research process all the way from the 1-to-1 or 1-to-2, this kind of skill, to prove this kind of skill or this kind of material process could make sense. So that's what I appreciate. And also, we established a digital futures culture here over the past 15 years. Every year we are doing a lot this kind of pavilion works.
Yeah.
Including from last year, Norman actually coming to introduce the RAM robotic RAM project. That is fantastic. And this year we'll go to 2.0. I think, and actually, what my team consider, actually, we have like a lot of real scenarios which can introduce this kind of rammed earth technology into reality. But how to achieve will be still have a long way. It's not easy because all the protocol and the parameters should be proved before the real construction could happen. So that's not easy. We still
But we
need
do this, Philip. We do this. We now
you're doing a
we
lot,
test
right?
the material and
Okay.
yeah.
Yeah, that's great. So that's why the
Yeah.
communication and collaboration will speed up a lot of like
Yeah.
from research to practice process. I think looking forward, this could be happen this summer. Yeah, yeah.
Maybe also one point I want to bring your attention. So when between architects and engineers. So let's say, because I said the engineers, they are focused on their fundamental research.
Mhm.
And the architects, they are focused on the experimental research. So,
Mhm.
so when you go to Rob Ash, there are so many interesting ideas,
Yes. Mhm.
but then they stop. They go to the
Yeah,
next experiment.
exactly.
So they don't
Exactly.
go deeper,
Yes.
deeper, because this is, and you have to bring both together.
Mhm.
This is why this interdisciplinary works. So seeing an experimental approach, okay, this could work. And then you need the engineering methods to
Yeah,
really go deeper and understand, and then
exactly.
make this technology really run. This
Exactly.
is what I say. Architects, they stop too early. They go to the next, and they are happy to have seen, look a pavilion, and then we go to the next pavilion. This is this. But this is our genetic code. We go from project to project, and we have to find more repetition in the processes.
Mhm. Great. So I would like to give the
audience.
opportunity to the floor. If the students have any question, it's a great opportunity. You can put forward to Professor Kloft, and he will give you some feedbacks. Any question?
Yeah, they are shy. Oh no.
Oh,
Okay.
great. Yeah, please go ahead. Yeah, you can go to the front because the microphone is on the in the front.
How many students are there? 40, 50?
Okay, yes, something more or less. We have a lot. It's international students. Yeah, please go
Hello.
ahead. Yeah.
Hello, Professor. Thank you very much for your sharing. And yes, you just mentioned we need to maybe to create a loop to organize all the everything you mentioned, like the material behavior and the fabrication process, even the architecture expression. So my question is, in robotic or additive construction, especially at the full skills, do you think the design should become more feedback driven in future, like using data from sensors and from the material performance, and maybe we need to give a feedback and immediately and to also to update our design, and what should be the biggest challenge in building this kind of closed loop in design to fabrication system? Because in my observation at the additive construction experience, so in many small skills, we are always rely on maybe some experience and also technical tolerance. I think is not just so intelligence enough. So because we urgency to build up a system or the process which can be repeated or be copied, like using additive manufacture. Yes, that's my question.
Mm-hmm. Yeah, thank you very much. Let's say your questions are maybe on two levels. So the question on design, starting maybe with this question, I think we are now in a point in our development where we have to really go back to the needs. So that means what kind of structures, what kind of buildings we really need. And when I told before, I'm now in Venice, and it's fascinating that this city of Venice, what is the fascinating part of the city of Venice? You could say these are all the buildings staying around, but each building as a single building is not that fascinating. There are, of course, the old churches and so on, but it's the whole arrangement of the buildings, and it's the whole arrangement of the city. There is a city which is made for humans. So there are public spaces, there are small streets. For me, this is immediately something I go out here and I start to relax because I'm in my natural speed. So there is no bike which collapses with me, no car, no train. So I can really walk, and everybody walks. So you can adapt, and you can. This is your natural speed, And we lost this in our cities. So I was last year in Tokyo. I was also years ago in Tokyo, and I recognized this year really extremely that how this city was made for or is made for the streets, and what kind of role we as humans play there. Not really a role. And so we are working now on it's called a research project. We just starting this. It's called Respace. Respace. we want to give back the space to the people. And the idea is when maybe I was not in China for 2011 last time, I would say, 15 years. How it developed in the last years, but we really compact and make our cities more and more dense in the building with the buildings, but the infrastructure space is just on the ground floor and underneath, so the subways. And so all the people has to, and all the different speeds with cars and trains, and have to find ways how they move each other. And we go in the third dimension with the infrastructure. So we start now to do new designs to relax really hotspots, traffic hotspots in the third dimension, but we bring not the cars on top, we bring the slower motion on top. So a little bit like High Line in New York. I don't know if you have this idea in your mind. And this is perfectly for digital fabrication, additive manufacturing. So we are able to scan the whole environment. We have the digital models. We can do form finding, which is really adept. We have the printing technologies which can have these unique solutions. So this is one thing. The other thing is the coastal protection, flood protection. So we have to find the really need for our new designs. And then the designs coming out of a logic of form. When I have a beam and the reinforcement is put along the tensile forces, then of course the logic of reinforcement. But if you be in a city and want to respace, then it's the logic of how a city and how we as a community work. So this is, I think, very important. You mentioned, Philip, that you have 4 different departments. So also the collaboration between all these are very important, you know, is in the future. And then this other question was on, yes, then this is more a kind of a control. I see absolutely that we have to have adaptive processes. So the environmental conditions are always changing also over the day. I still keep the idea that we will have our construction sites also in the future as our factories, but they should be smart factories, and they should be, after 2-3 years, they should be flexible. So to go to the next site. But ideally, like in former times with the construction huts, maybe there are teams going around, you know, so that you don't find again the totally new people. So you go with your team to the next site. So this is maybe a new thing on collaboration. And then planning could be also much more interactive with manufacturing by all the sensors. Yeah, of course. Yeah. For example, if you have a coastal protection, so a line of 100 meters, 200 meters, you know, in our thinking now, we have to develop the whole geometry for 200 meters we do, and then we try to control the robot to be precise for a length of 200 centimeters plus minus 10 millimeter. Come on, this is not possible. So then start to print, and if you see there are 5 centimeters for coastal protection, doesn't matter if there are 5 centimeters more or less. So start to print, and then you correct during printing. You know, this is the future.
Mm-hmm. Great, good. Maybe one more question, the last question. Any student would like to ask? Okay.
How?
Welcome.
Thank you, Professor Kloft. Can you hear me?
Yeah, I can hear you.
Yeah. Thank you for your wonderful presentation. And I have one question. Mainly focus on your research project. You have shown us many research projects about the short clip printing. And it seems that
in your institute, you mainly focus on shotcrete 3D printing rather than the extrusion-based 3D printing. Except for the Yanan's research, he did a good job about the in-session 3D printing. I want to ask, is this research direction related to your background as a structural engineer? And because more generally, what is your view on extrusion-based 3D concrete printing? Maybe it seems that you prefer to shotcrete the concrete rather than extrude the concrete. Can you explain why? Thank you.
Yeah. So thank you, Hal. I think there is not let's say behind a strategy to avoid extrusion. I'm saying for us, extrusion is just to turn off the air. So we can we can from zero air, then it's extrusion, to fully air, then it's fully shotcrete. So we are able to vary. But because this is right what you're saying, because I'm a structural engineer, so for me concrete and especially working with this high performance concretes means to lose less as possible, and this means reinforcement. First, it means a shape which is curved. Double curved is the best, but of course you cannot everywhere use double curved shapes. But then also the reinforcement integration is needed, and so the shotcrete is the best for making really to compact the concrete. So otherwise we have these cold joints in the extrusion technology. Is more than a masonry. We handle this more than a masonry structure with the calculations, and by using air in the shotcrete, we also are able to, and the robot to really spray fully around the reinforcement, the concrete. So I didn't show columns. We worked also a lot on columns. And for me, this is the most future technology. I don't know why companies don't start to use this. Be honest, maybe it's too intense investment, and it's not a fast success. So it's not that okay, let's start and print a house, and so like the extrusion guys are doing, and but this will fail. So people, they like it now, maybe this wave-like surfaces, but I think the shotcrete has on the longer run much more potential. Yeah, will not fail, but maybe it's also here a combination. We're also thinking on using, let's say, the extrusion for more form given, and then the second layer could done with shotcrete. Also, this we are working on.
Great. I actually appreciate this kind of shot concrete or shot earth technology because the materiality is fantastic. I remember Herzog Damelonde used to design a museum. I think it's a fantastic service, which is based on this kind of spray concrete. The texture will be great. So, and also it's very good for the institute formwork, which could be controlled well. I think we'll have a great opportunity in the real practice. Probably we can try in the future in China.
Yeah, let's do it.
So my team is super strong in the practical part. I think looking forward to collaborating with you and your team in the future. So I think it's time we should wrap this tonight's lecture. So thanks so much, Professor Kloft from Venice, to make this lecture. I think I can remember last year I was in Venice this time for the architecture biennale. So this year
exactly.
This
is art this year.
Art biennale. So it's a fantastic moment. Let us to remember this special moment for Professor Kloft. I think thanks a lot for your fantastic lecture. Looking forward to invite you in the near future to visit Shanghai, and looking forward for the summer workshop. And
yeah, super.
Your team will collaborating with us in China. That would be a fantastic opportunity. So thank you so much.
Thank you very much, Philip. Thank you, Hao. Yeah,
keep in touch.
And
yeah,
the students, and we keep in touch. Yeah, thank you very much. Bye bye.
Bye bye bye.
结束，是，别给他查，结束会议了，结束。